Okay, so in this chapter, we will study the elementary fluid dynamics through the Bernoulli equation. You are familiar already, I think, with this term, and we will see together how the Bernoulli equation is widely used to solve several engineering problems. So to start with, okay, we will start to define what is a streamline, because Bernoulli equation will be applied along a streamline, or we can apply Bernoulli perpendicular to the streamline. So we should first define what is a streamline. So if you have a fluid flow and you observe it, if you track your particle if you want, and you can put, let's say, smoke, or you can put particles that can be followed. Then, if you take a picture at any instant, okay, the passes of particles you will have are streamlines. So by definition, streamline is a line that is tangent to the path. So imagine that you have smoke, for example, and smoke within the flow, or you can put a color sometimes. Sometimes I put colorful particles in red, let's say, to be able to visualize the flow. So if you take a picture at a certain instant, you will see lines. So these lines represent the trajectories of particles, and you can consider then that these lines are formed by the velocity vectors of your particles. So by definition, your streamline is just obtained by joining tangent lines, so by joining velocity vectors. Okay, so this is why we say that in this case we can define the streamline in this way. So if we have the streamline can be defined at any time t. So for any time t, if you take a photo, then all particles, if you want, you are seeing them at one instant. Okay, this is why we do it as a comparison with a photo, because when you take a photo, everything in your photo is taking place at the same instant. So we say that at each time t, we can have a certain series of streamlines, and then these streamlines represent the tangent to the path, okay, at any point. This is why if you want to get, we will see together after, that if I want to get the equation of streamlines, let's say y as a function of x, to plot them, I go back to the definition. What is the definition? At each point of my streamline, the slope is equal to the velocity, because we said the streamline can be drawn by just joining velocity vectors. So if at each point I draw the velocity vector, then by joining these points, I can get my streamline. Okay, so by definition, the slope of the streamline, which is dy by dx, is equal to the slope of velocity, is equal to the if you want velocity, which is equal to the slope of the track. So it's equal then to v over u, okay, where u and v represent the components of velocity. In general, when you see this u, v, w, okay, you have that u represents the component of velocity along x, small v represents the component of velocity along y, and w represents the component of velocity along z. So if you have a 2D flow in xy, let's say, then you can write that dy by dx for your streamlines is defined as v over u, okay, because the velocity vector is tangent to the streamlines. Now, what is the Bernoulli equation? The Bernoulli equation is an approximate relation between pressure, velocity, and elevation, and is valid in regions of steady incompressible flow where net frictional forces are negligible. So if we do the analysis of this sentence, we have a lot of assumptions, because first, the Bernoulli equation that you will derive will only be valid in steady flows. Incompressible, we will derive also a Bernoulli that can work for compressible flow, but the known Bernoulli equation is applied for incompressible flows, and we don't have friction, or friction is negligible. Okay, and in general, this takes place far away from surfaces, because if you remember in chapter 1, when we consider flow over the surface, we said that as due to non-slip condition, at the surface level, we have velocity of the flow is equal to the velocity of the surface, and we have shear forces. So you have development of shear forces at this level, and therefore your shear forces, okay, will try to oppose motion, and this will create a certain friction and losses. Okay, this is why we cannot apply Bernoulli close to surfaces. If you want to apply it, we apply it far from surfaces. Why? Because if we are far away from the surface, we can neglect viscous effects that are dominant in this region. Okay, so in general, as you are far away from the surface, the inertia forces, which means forces related to acceleration of the flow, will be much more dominant compared to viscous forces. Okay, this is why, for example, if you deal with a pipe system and you want to do Bernoulli equation, you just apply it at the center line. You don't apply it near the pipe walls. Okay, and we will see that Bernoulli equation is very simple, and it's like its form is similar to conservation of energy. You have, if you have taken dynamics course, you have seen when we can apply conservation of mechanical energy. So Bernoulli is similar to conservation of mechanical energy, but now instead of we are dealing with a fluid instead of dealing with a solid. So now let us see together, okay, how to derive the Bernoulli equation and what are the main assumptions that we should consider. So first, as we said, this approximation will be used in flow regions that are far from surfaces, plus, and this means when we say regions outside of boundary layers, this means that we are in regions far from surfaces, because whenever you have contact between a fluid and a surface, we will have the formation of what is called boundary layer. What is a boundary layer? The boundary layer is a region where you have transition, because your flow, let's say far from the surface, is uniform. However, here, if you have a fixed surface, for example, you are forcing the flow to have zero velocity here. So you'll have a certain region of transition where viscous effect will be dominant, that will give you a certain velocity profile to go from zero to the uniform profile. So this region is called boundary layer. So if you want to apply Bernoulli equation, you should make sure that you are far away from boundary layers. And also, we should not have wake regions. What do we mean by this? So if you consider the following example, you have a fluid going over an airfoil. Okay, so then what will happen is that you will have streamlines. If you take a photo, if you do visualization of your flow through smoke or through red particles, and you observe the trajectories, you will see that the flow will do a certain separation at this level because of this contact with the airfoil. Okay, so you have streamlines will go apart here, and you have a certain region after your airfoil that where you don't have streamline. So here you don't have flow in this part. This is called a wake region, and Bernoulli equation is not valid in it. So I should be far from the wake region. So if you want, I should be far away in a way that the wake region will not affect my streamline. Okay, so in general, whenever you have separation regions, wake regions, or you have boundary layers, you should get far away to be able to apply Bernoulli. Okay. Now, in Bernoulli equation, the main forces are pressure forces and gravity forces. And this is what we have already considered, if you remember before, when we did the analysis of fluid flow in static case, we considered pressure forces and gravity forces. Okay. So let us see how to derive the Bernoulli equation. Okay. So first, we will consider a two-dimensional flow, and the acceleration then can be decomposed into components. Because you know that for a fluid, okay, for any particle in motion from dynamics, you know that if I have a curved motion, okay, I can divide my, if I want to write the Newton law, I will write it in two directions. I can write it along ut, which is the tangent direction, and along un, which is normal to the path. Okay, so in case I want to apply Newton law, if you want, I will divide my directions into tangential and normal. Now, in this case, we say that the acceleration is decomposed into streamwise acceleration, that is along the streamline, and a normal acceleration an, that is normal, which is perpendicular to ut, and always directed towards what is called the center of curvature. So again, from dynamics, remember, for example, if I have the following curve, at each point, I can define a radius of curvature. How can I do this? So if I am at this location and I am moving, okay, I can consider that for this small part, this small segment can be approximated as an arc of circle, okay? This is why when I am here, the center of curvature will be at this point, and my normal acceleration an will be directed towards this point. If I move to another location here, when moving on this segment, I can consider that this segment is on another circle, and the radius of curvature is equal to a new value here, okay? This is why at each position, you have a new radius of curvature, and you have new ut un unit vectors. So ut un vectors are changing in direction for curved surfaces. So, and you know that, from dynamics, that the expression of normal acceleration is given by v square over the radius of curvature. Okay? So now, we can say that, by definition, why we have streamwise acceleration. an is due to the change in direction. So if you remember in dynamics, you have at and an. an is due to change in direction. So I cannot change direction without having a normal acceleration. While at is for change in speed, because at by definition, a tangential, is dv by dt. Okay? So at is the acceleration component due to change in speed, and an is the normal acceleration component that is due to change in direction. Now, if in case I have particles moving along straight lines, then I don't have change in direction during motion. The normal acceleration will be 0, and I will just have a tangential component for the acceleration. And I can verify this also from this relation, okay? Because if you have a straight line, what is the radius of curvature? Who knows what is the radius of curvature for a straight line?
Infinity.
Look, whenever you have an arc, you can get a certain center. But when, as your arc becomes more flat, your center will be far away. So when you take a straight line which is completely flat, your radius, your center of curvature will be at infinity. This is why we say for a straight line, r tends to infinity, so an is 0. Okay? Yes, exactly. Okay. So now, let us consider a flow, a fluid flow, and we want to characterize it, characterize the velocity with respect to position and with respect to time. What I want you to know is that the main difference between the dynamic approach that you already know and now what you will do with fluids is that in fluids, okay, you can have acceleration even if you have a steady application. So what do we mean by this? You can have change of velocity with respect to position and not with respect to time. So if you look, if you are concerned, let's say with the flow within this nozzle, for example, okay, then what will happen is that when I say steady state conditions, this means that I don't have variation of velocity with respect to time at a certain point. Okay, so if you are observing the following nozzle here, when I say it's a steady state application, this means that if I look, let's say, at a particle at the inlet at this location, whatever is the time I consider I will measure the same velocity. But this does not mean that if I change position, if I measure the velocity of this particle, I will obtain the same result. This is why we say, because when we take a fluid flow, then we are not just concerning one particle, we are concerning considering a field of particles. Okay, I have variation with position and I have variation with time. So when I consider at a certain position measurement of velocity over time, and I don't have any change in velocity with time at any location, this means that my flow is steady. Okay, but this does not mean that my flow is not accelerating. You know why? Because for the nozzle, for example, because of steady conditions, everything coming in will get out. So you can say that m dot n, the mass flow rate that is coming in, is equal to the mass flow rate that is getting out. And you know what is the expression of a mass flow rate? The mass flow rate can be written as density times acceleration times velocity. Okay? And since it's an incompressible flow, so I will write rho A1 V1. This is section 1. This is section 2. So rho A1 V1 is equal to rho A2 V2. Since it's an incompressible flow, rho will cancel out. Now I have a nozzle, so what is happening, the area is decreasing as I am moving from the inlet towards the outlet. So the velocity should increase. So the velocity, as I move through my nozzle, the velocity will increase. So here I say I have acceleration, okay, with position, not with time. Okay. However, if I take the other approach, if I just follow a particle and consider how it's moving, of course it's accelerating with time because the particle is taking several positions of the flow as it's moving from inlet to outlet. So in dynamics part, you were just considering particles motion. You were not considering what is happening for a field. In fluids, in general, we consider flow fields. So let's say I define my interesting zone is the nozzle, and I want to determine at any point of this nozzle, at any cross section, what will be the velocity. So when your interest is a flow field, then here you will talk about acceleration with space and acceleration with time. However, when you just follow a particle, you just talk about acceleration with time. You just have one variable. However, here for a flow field, the velocity field V is defined function of position and function of time. This is why, okay, when you want to define acceleration, Acceleration is known to be the derivative of velocity with respect to time. And since here I have two variables, okay, of interest S and T, you know that in mathematics, whenever you have a function that is depending on different variables, the differential dv, okay, will be equal to del v by del s ds, where s is the position variable, plus del v by del t times dt, where t is the time variable. And now, since you know that your acceleration a is defined as the derivative, this is called the total derivative, and del is the partial derivative, okay? So we know that a is the total derivative of v with respect to time. The total derivative of v with respect to time is del v by del s times ds by dt, okay, plus del v by del t. So all I did to go from this equation to this one is that I divided by dt. So I divided here by dt all sides. dt here will be simplified. So I get the following result. And this is very interesting. This result will tell me that acceleration in a flow field, okay, is decomposed into two terms. This is called the total acceleration. Okay, this term is total acceleration. This term, okay, you know this term is due to what? This term is due to change of velocity with position. So if you don't have, so this is why I told you in flow fields, we talk about acceleration with space and acceleration with time. And the total acceleration is equal to the summation of both. So this term is called local acceleration or acceleration with space. So acceleration with space. And this term is called, this is the acceleration with time. Now, in case you have a steady application, whenever we say steady, this means that we don't have variation with time. So if you take a photo of your flow field at any time, you will exactly obtain the same result. So when we say steady flow, this term automatically will cancel out, and then you will only have acceleration with space. You can have cases where you don't have acceleration at all. No acceleration with time, no acceleration with space. A very simple example is that if you have a steady flow through a straight pipe of constant cross section. So if you have flow in a straight pipe of constant cross section, because of equal inlet and outlet flow rates, because you are in steady conditions, and since A1 is equal to A2, so then you can deduce from conservation of mass that also V1 will be equal to V2. So in this case, for the steady flow in a pipe, nothing is changing with respect to time and nothing is changing with respect to space. Because if you move along this line, you will have everywhere the same velocity. Okay, then we say in this case we have zero acceleration. So no acceleration with time, no acceleration with space. Okay, now in order to derive the Bernoulli equation, we will start from Newton law. Newton law applied on a certain particle. Okay, so what we will do then, we will consider the following. We have a particle. What are the forces acting on it? As we said in Bernoulli equation, what are the main assumptions? No friction. Okay, no friction forces, and the particle is just subjected to the effect of the weight and to pressure forces. Okay, so what I will do then, I will apply Newton law along UT, which is the streamwise direction, and UN, which is the normal direction. So if I apply the Newton law along tangential direction or streamwise direction, I can write sum of forces equal mass times AS, okay, which is the acceleration component along the tangential direction. Now, what I will do, I will just consider what are my forces. I have pressure forces on these sides. So first, we will consider along the streamline, what are the forces? You know that you have pressure forces on all faces. So here on this face, let's say you have P dA. On the following face, you have P plus dP times dA. And you have the gravity force. So now we will project the gravity force along the streamwise direction. And we can consider then that angle theta represent at any location the slope of your curve. So because if I consider at any location the tangent, how to calculate theta? Theta is simply calculated as tangent theta, okay, is dz by dx. Okay. Now, if we apply Newton law along tangential direction, what do we have? We have the pressure force on this side plus PdA. We have the pressure force on this side, so it's minus P plus PdA plus dPdA. And we have the projection of the weight. And look, the weight is always vertical. So it's doing, if we represent the weight here, okay, this is our weight, it's along DZ. Okay, this is W. And as you can see in the figure, theta represents the angle between the tangent line, okay, and the horizontal line. And so if I want to determine what is the angle between the tangential direction and the weight, this angle will be pi over 2 minus theta. So if you want to project the weight on the tangential direction, or you do cosine pi over 2 minus theta, or you do sine of theta. Okay? Because you can say also that since the weight is doing pi over 2 minus theta with ds, okay, then along the perpendicular to ds, it will do an angle of theta. Okay, so because as you can see here, this is the weight, this is the perpendicular to ds. Okay, so if this is pi over 2 minus theta and this is 90 degrees, then the angle between the weight and the normal direction un is equal to that. So the projection on UT direction gave me the following, and this should be equal to m times AS, which is the tangential acceleration. And we know that the tangential acceleration, okay, can be written as AT. We know that AT is by definition, okay, related to the derivative of velocity with respect to time. Okay, but we can write it in another way, because you know that we have that if we relate to position, okay, we know that ds by dt, velocity by definition, is the derivative of position with respect to time. Okay, so if I want to eliminate time, I don't want to consider time in my equation, I can replace from ds by dt equal v. I can write that dt is equal to V over ds. Sorry, ds over V. Okay? dt is ds over V. And now, if I replace dt here by its expression, what do I get? I get that the tangential acceleration or the streamwise acceleration, as or at, is equal to v dv over ds. Okay? So you can replace the acceleration along the streamline by v dv over ds. And this is what they did here. So sum of forces along the tangential direction or along the streamline is equal to mv dv over ds. And now, in the next step, okay, if you look at your figure, sine theta represents what? If I look at this triangle, as we said, theta is the angle of the slope of the line. So it can be related to, from this figure here, I can just say that sine theta is dz over ds. Okay? So I can replace in my relation here, I can replace sine theta by dz over ds. And of course here I have plus PDA minus PDA, which will cancel out. So I will end up with the following, minus dPDA. And for the weight, what is the weight of this element? The weight of this element is its mass times G. And since I am considering an elementary element here, the mass is equal to rho times the volume. And its volume is dA, the elementary area, times dx. So I can replace m by rho times volume, which is dA dx. And of course, I multiply by g to get the weight. So if you replace sine theta by dz by dx, and you replace your weight by rho g dA by dx, this is what you will obtain. And of course, also I will replace the mass here by rho dA dx. Now, a lot of terms will simplify. dA will cancel out from all sides. And concerning here, you have ds over ds also will cancel out. V dv is just equal to the following. It's half of dv squared. You know why? Because you can easily demonstrate this. If you have d of v squared, okay, so it will be equal to, this term is 2v dv. 2v, it's like you are differentiating. 2v dv. And you have 1/2, so over 2. 2 and 2 will cancel out. So you can replace v dv by half d v squared. Okay. Now, if we observe our relation, we obtain the following. We obtain that minus dp minus rho g dz plus, and this term will replace it by rho times half dv squared. Okay. If we take these terms to the other side, we get the following. We get that dp over rho, and we divide by rho all terms. dp over rho plus half dv squared plus g dz equals to a equals to 0. And this equation is very important. From here, we can derive Bernoulli equation. Because if you go from any position 1 to another position 2, and you want to relate the variation of pressure with the variation of velocity, all you have to do is to say that since this function is a constant, if is equal, to 0, if I integrate it, I should get a constant. Okay, so integral dp over rho plus integral v squared over 2 plus integral gz is constant. Okay, and therefore I can say that in case I have a compressible incompressible flow, what will happen when I integrate? Okay, so when I integrate each of these terms, g is constant, so when I integrated dz, I got z. Okay, And when I integrated dv square, I got, and this is over 2, I got v square over 2. I still have this term, integral dp over rho. In case rho is constant, so if I deal with incompressible flow, I can take rho outside of the integral, and I can replace integral dp by p. Of course, delta p, because when you integrate, whenever you integrate, if you integrate dp, what do you obtain? Integral dp is p plus a constant. Okay. So all constants, you can lump them to the other side. This is why you can write the following: p over rho plus v square over 2 plus gz is a constant. And this is only valid if we are in a region, as I told you before. Remember always your starting point. You said I am neglecting friction. Okay. So, and I am doing this along a streamline. So I cannot move from any point to any other point. My analysis was done by moving along a streamline because I applied sum of forces equals sum of forces along the streamline equals to m times a tangential. So this equation is valid if I move from one point to the other along a streamline. And how I can interpretate physically this equation? I can relate each term to a certain energy. P over rho is related to the energy of the fluid. It's due to the pressure of the fluid. Okay. V square over 2 is related to the kinetic energy, and this is related to the potential energy. So this Bernoulli equation is equivalent to conservation of energy. So we can say that the sum of kinetic, potential, and flow energies of a fluid particle is constant along a streamline during steady flow when compressibility and frictional effects are negligible. Okay, so these are the conditions to apply the following relation. Now, in case it's incompressible, you still can apply this, but you have then to be able to solve, you should know rho function of P. So if you have an incompressible fluid, a compressible fluid, you should be able to get rho function of P. Then you can proceed. You can integrate this function. And this one is used in case you have an incompressible fluid. So now, if I move from any point 1 to another point 2, since this term is constant over the streamline, this means if I apply this term at point 1 or at point 2, I get the same result. So I can say that P1 over rho plus V1 square over 2 plus GZ1 is equal to P2 over rho plus V2 square over 2 plus GZ2. Okay. Any question on this? Someone was asking me at a fixed point V is constant if I am saying it's a steady flow. Okay. If the flow is not steady, you can have at the fixed point V variable. So when they say steady application, this means if you look at a fixed point, nothing will change. Okay. But in transient application, it can change, of course. P over rho